Welcome, class. In this video, we will go over lesson 9.3, exponential growth and decay. Now, a basic exponential function will follow this format. It'll equal some starting number, 1 plus r, if this is a growth function. Let me go back and actually add that. This will be a growth exponential function. 1 plus r raised to the t. Typically, r is going to be some percent increase written as a decimal. And t represents time in years. A will be the starting amount, also known as the principal amount. We will also have a decay function. It'll follow a similar format of A, some starting amount, 1 minus R. This would be the key difference. Let's graph both functions. Let's do a growth function first. Let's say we have $2,000 in a savings account, and it's growing at, or maybe $2,000 in a stock, a share price. Let's say it's increased by 10%. 10% will be 0.10. And let's see what it's worth after 1 year. Because if we're actually growing it for more than 1 year, there's another equation we want to use called a compounding interest formula. So let's see what it is after just 1 year. Now, I'm going to change the scale. Let's see, we're going to have to zoom out here to see what it actually looks like because we're doing it 2,000. There we go. Oh, I actually made a mistake here. That's actually, we can find the actual value, which is about $2,200, excuse me, to actually grow it, just to actually graph it. Let me show you here. Let me graph it as X. There we go. And now we're going to have to zoom in again. I apologize. I was getting ahead of myself on this lesson. We're going to be finding how much something is worth after so many years. Here's our typical exponential growth function. You see it here. It's growing very quickly here. It has a y-intercept of 2,000. We have to scroll up here. $2,000. Here's the y-intercept right here at $2,000. And it's just going to keep growing. Of course, we used a very large number here, so it probably wasn't the best example for a graph. Now let's try another value. Let me zoom out here so it'd be easier to go back. I'm going to pick a much smaller number. Let's do a decay function. Let's say we had a value starting at $100, and we have something that's decaying over time, which I'll call it X in this case. Let's say a rate of decay of 10%, meaning something is decreasing at 10% per year. Here's our typical decay function. And there we go. See the line in blue? Here's our decay function. Here's the y-intercept of 100. The starting value here will be the y-intercept, 2,000 for one and 100 for the other. Because it's a decay function, it's getting smaller. In this case, it's approaching the x-axis. But if we zoom in, you would actually see that it never actually reaches the x-axis. It just gets closer and closer. But it never actually touches the x-axis. Now let's look at the worksheets. Okay. Our first example here says, the population of a city is increasing at a rate of 4% each year. There's our R value. This would be our R value right here. R is going to equal 0.04. 4%. If you're not sure how to convert a percent to a decimal, if you ever forget, percent means out of 100. Percent or per century means you just divide it out of 100. So 4% will be 4 divided by 100, which of course we will get 0.04 or 400ths. In 2000, there were 236,000 people in the city. Write an exponential growth function, so it's 1 plus r. Growth function tells us it'll be 1 plus r. To model this, then find the population in the year 2009. So here's our basic function right here. Y equals a times 1 plus r raised to the t. Our starting population is 236,000. We're increasing at 4% a year, and time, of course, is in years. Starting in 2000, we're trying to find the population in 2009. So what would t be? What would we plug in here for t? What year? Well, it's going to be 9 years later. So we plug in the value 9. And we just type it into a calculator, and we got right here 335,902. Let's look at a decay function. Population of a city is decreasing at a rate of 6% each year. In 2000, there were 35,000 people. This is obviously a town of 35,000 people. Write an exponential decay function to model this, then find the population in 2012. Again, we have a starting population of 35,000. It's 1 minus the 6%, which is 0.06. And the time here from 2000 to the year 2012 is 12 years. Here in the example, they just actually did 0.94 because they did 1 minus 0.06, which we can type that, or we can type it all at once in the calculator. But of course, 1 minus 0.06 is 0.94. Here we entered it in for 12 years, and we found the population decreased from 35,000 to 16,657. Let's look at the first example. Number 1. Write an exponential growth function to model the situation, then find the value of the function after the given amount of time. Annual sales at a company are $372,000 and increasing, that's important, at a rate of 5% per year. And what would it be after 8 years? We know the starting amount is going to be 372,000. It's increasing, so it's 1 plus r, and r is the 5%. T, of course, is the 8 years. So let's type it in here. We're starting with 372,000. 1 plus r, which is 1 plus 0.05. And we're going to raise it to time years, which is, of course, 8. Now we're going to type this into a calculator. Let's get our calculator here. Let's see here. We should pull up into a scientific calculator. Let's see, where did it go here? There we go. Okay. We're starting at 372,000. We're going to multiply it. I'm going to use a parentheses here. Parentheses. 1 plus 0.05. Close the parentheses. Now that's 1.05, the 1 plus 0.5. And we're going to raise it to the 8th. Equals, here we go. And because this is a population here, we're going to go ahead and we'll round it to like the nearest whole number. 549,632. Oh, excuse me, this is in dollars. So we're going to have to change that again. 549,300 and something. I'm going to have to pull that up. I forgot what the 549,613 and 43 cents. We're going to round it to 43 cents. And 43 cents. So the sales at a company increased at a rate of 5% per year. And after 8 years, they were making $549,613. This would be a good example of it could be a value of a company. And nowadays, it could be even the salary of a CEO, and getting a 5% increase each year for 8 years. This would be his annual increase. Well, his annual salary after 8 years. The next problem, number 2. Population of a town is 4,200, and it's increasing at a rate of 3% per year for 7 years. What is the population in year 7? Let's see. Y equals the starting number of 4,200. It's an increasing, so it's 1 plus 0.03. for 7 years. For 7 years. Let's type that into our calculator. You clear it here. We have 4,200 times, parentheses, 1.03, because I'm just adding it, and we're raising it to the 7th year. And we get, now this is people, so let's round to the nearest whole person, which is 5,165. And we'll write persons here. Always have units on word problems. That's the population of the town 7 years from now. Number 3, write an exponential decay function to model each. So decay would be 1 minus the r. Number 3, monthly car sales for a certain type of car are $350,000 and are decreasing rate of 3% per month for 6 months. Now, normally this equation, time is in years, but we're giving a rate in a month and we're asking in over months. So we can just keep them, we can keep time in months for both and it won't mess up the answer. Sometimes we have to do a conversion from months to years, but because everything is rate per month and we're asking for a month, everything is okay. So we're starting with 350,000. It's 1 minus 0.03, and it's raised to the 6. A 3% decrease for 6 months. Let's clear here. So we have a 350,000 in annual sales. A decrease, so it's 1 minus 0.03, which is also 0.97. And we'll raise that for 6 months. What would this be? So 291,540. 291,540, and this is in cells, so we'll go to 2 decimal places, which is 20 cents. Number 4, and a chat room has 1,200 participants. That's the starting number, and is decreasing at a rate of 2% per year for 5 years. Now we're back to using time in years. Our starting population is 1,200 persons. It's decreasing, so it's 1 minus r, 1 minus 0.02, and it's raised to the 5th year. What would the population be after 5 years? So it's decreasing. Let's see. So population of 1,200, decreasing at 1 minus 0.02, which is 0.98. So each year the population is 98% of the previous year because we're decreasing it. And we're going to do this for 5 years. The population is 1,084, or is it 1,085? We're going to round it, and we'll round it to 1,085 participants. We can't have half a person. It's 1,085 participants. Now for the next section of exponential growth and decay, now we can start actually figuring out how much something is worth with compounding interest. Before we were doing it for simple interest, for very simple problems. Now, a compound interest example would be you buy a stock, similar to the very first example we talked about. Let's say the stock price was, I think it was the $2,000 we said, and it grew at 10% each year. But maybe we didn't get, maybe we didn't take into consideration that the stock was, instead of 10% for the whole year, we could actually look at its value if it was being raised per quarter or per month. It was increasing, where maybe 10% was like an average for the whole year. This way we can get it more accurate, because no stock's going to increase at the exact same percentage each year. Perhaps it's increasing or paying a dividend every so often, every few months, every month, every week, every other week. So we're going to start looking at what's known as compound interest. Okay, now let's look at the equation for compound interest, which would be this one right here that I'm highlighting or boxing. Okay, it'd be easier just to do an example problem. Okay. Now, let's say we have some money we're going to put into a bank. Let's say that that amount is $10,000. And this amount of money is going to be in an account that pays an interest rate of 5%. And we'll be compounding this interest every quarter, a quarter, which means it's going to happen 4 times in a year. So if this is let's say we're not getting normally we do the 5% at the end of the year. Now we're just going to be breaking up the amount of money we're going to receive every quarter. So instead of doing 5% of $10,000 at the end, we're just going to do a fraction of the 5% every quarter, which means we're going to be doing it 4 times each year. 4 times each year. And I'm going to ask after, just for an example, let's do it after just 1 year. 1 year. The basic equation, the amount of money, is going to be the principal times 1 plus the interest rate divided by the number of times we're compounding it, raised to the t, but it's going to be now to the nt. N is, again, the number of times we're going to be compounding the interest. So let's say we have an amount of $10,000. The interest rate is 5%. I actually wrote 0.05, which is good. And we're compounding it 4 times a year. And NT, 4 times T is the number of years, which is 1. 4 times 1. Let's see how much this interest is going to be. Let's get out the calculator. Let's see here. It's a free app, so sometimes it'll ask me. Whoops. Let me shrink that down. There we go. Okay, so we're going to start with $10,000. Sorry, I'm about to move this over so we can see on the screen here. $10,000. Just want to make sure. So at $10,000, and it's going to be 1 plus 0.05 divided by 4, okay, raised to the 4th. And we're going to have $10,509 at the end of 1 year. $10,509. Now let's think about that. If we just did the straight interest equation of 5%, will we have the same amount of money? If you remember, the basic equation for simple interest is P times 1 plus R raised to the T. If we have $10,000 and we have an interest rate of 0.05 for 1 year, what would that equal? Well, if we did the math, we'll find that we're going to have $10,500. Notice the difference in the numbers. By compounding the money more than once per year, you actually make more interest. You make $9 more in interest. It may not seem like a large amount, but if you compound this over several periods, over several years, the money grows much faster. This is why a lot of times when parents have bills, if they borrow money, the money is not compounded once a year. The interest is not compounded once a year. It could be compounded monthly, or in the case of a credit card, it's compounded daily. Why would a credit card company compound the interest daily? It's because that way there's going to be more money. They can charge you more interest. If you didn't pay the credit card for a period of time, you would end up paying a lot more interest than if it were just compounded monthly. So credit cards are compounded. Typically, it's going to be daily. So N, when it's daily, is going to be 365 days. So for the N here, we would actually use N equals 365 if it were compounded daily. So let's take a look here. Now for the example problems, what we mentioned, A is the total, P is the original, R is the interest rate, N is the number of times interest is compounded, T is years. So here we're actually dealing the next kind of example, which is going to be a half-life. I'm trying to see if that's the best. Let me go. Here's the example I'm going to go over first. Here it is. Write a compound interest function to model $15,000 invested at a rate of 3% compounded quarterly. Then find the balance after 8 years. So the basic equation of $15,000 is how much we're starting with. 1 plus the interest rate of 0.03. This is 4 quarters per year. That's what the quarterly means. 4 quarters per year raised to the NT. This is the NT. N is 4, and T is however many years. In this case, it'll be 8 years in the problem. We did the math. We got this answer right here. $15,000 after 8 years compounded at 3% quarterly would be worth $19,051.67. Another example here we're doing is half-life. Now this is getting into science. Of course, math and science are really inseparable. Math is considered to be the most perfect science because math doesn't really change. We may come up with new formulas, but the rule 1 plus 1 will always equal 2 will hold true in mathematics. But in science, we keep getting updated information and the science keeps changing. So that's why only math is considered to be the perfect science. Here's a half-life problem. If you don't know what a half-life is, if you have so many grams of, let's say, carbon-14, it's this radioactive carbon element that we use to date living things that may have been alive maybe 5, 6, 7, 8,000 years ago. We can use carbon-14 dating. Things that are much older than that, we can't use carbon-14 because the half-life is too short. Okay, what half-life means is if we had, say, 100 grams of carbon-14 and the half-life is I can't remember, I think it's around 3,200 years. That means 3,200 years from now, the 100 grams of carbon-14 will amount to about 50 grams of carbon-14. And another 3,200 years after that, it'll be half that amount. Now, carbon-14's half-life is not 3,200 years. It might have been 2,800. I don't quite remember what the number was, but that's just the idea of half-lives. So here's an amount we have. P is the starting amount, a half-life of 0.5, and T is here going to be the number of years. So Ismuth 212 has a half-life of approximately 60 seconds. Find the amount of Ismuth left after a 25-gram sample after 300 seconds. We have to figure out how many half-lives is that. Each half-life is 60 seconds. How many half-lives go into 300 seconds? Well, we're just going to divide. 300 divided by 60 is 5. So this thing is going to be, there'll be half amount 5 times. So we're just doing the starting amount of 25 times 0.5 raised to the 5th, because there's 5 half-lives. And it says in this instance, after 300 seconds, there's only 0.78125 grams left. Now let's look at some example problems here. We have a 2 compound interest problems, and then we have 2 half-lives. Number 5, $17,000 is invested at 3% compounded annually for 6 years. So the time here is 6. The starting amount, the principal here, is $17,000. The interest rate is 3%, and it's compounded annually. Annually means how many times a year are we compounding it? In this case, it's just 1. So we're going to write our equation here. And because it's compounded annually, it is like a simple interest equation, but we're still going to use the full formula. Starting at $17,000, we're going to add the interest rate of 0.03 compounded once per year raised to the NT, which is 1 times 6. So 17,000 times 1.03 raised to the 6th, because it's 1 times 6. Let me make that as a parentheses and not as a dot. It may look like 16 there. Let's get our calculator. So we have 17,000 times 1.03 raised to the sixth. And we get 20,298 and 89 cents. So it's going to be 20,298 and 89 cents. That's how much $17,000 invested at 3% compounded annually for 6 years. Now we're going to do $23,000 invested at 2%. So here's our starting principal, the interest rate. Compounded quarterly means we're going to do it how many times a year? Well, N is going to be 4. And of course, T of here is going to be 8 years. So we're starting at $23,000 times, let's see, it's 1 plus 2% is 0.02, compounded how many times a year? 4 times a year, raised to the 4 times 8. What that means is it's going to be compounded 32 times, the 4 times 8. We're compounding it a total of 32 periods. So let's see what that number is. So we're going to do, usually it's a good idea to do the numbers inside the parentheses first, but I'll just do it on the outside because in this calculator I can see what we're typing, so I know we're not making a mistake in the order of operations. 1 plus 0.02 divided by 4, and we're going to raise this to the 32. And we get 26,979 and 99 cents. 26,000, I believe was what, 979? Yes. 979 and 99 cents. Now we're going to look at the two half-life problems. It says write an exponential decay function to model each situation. Then find the value after the given amount of time. We're starting with a 30-gram sample of iodine 131, which is radioactive. And incidentally, just so you know, the 131, that is just the mass number. The mass number is the number of protons plus neutrons. The protons and neutrons add up to 131. Now it has a half-life of about 8 days. And they're asking how much is left after 24 days? How much is left? Well, how many half-lives would that be? 24 days divided by 8 days. That's going to be 3 half-lives. 3 half-lives. So this thing's going to split half 3 times in a row. So let's see how much we're going to have here. Well, we're going to have a starting amount of 30 grams. And see, the 0.5 we're multiplying is a half-life. There's half left. Like after 1 half-life, it would be 15. After 2 half-lives, there would be half of that, which is 7.5. And then another half of 7.5. Just so we can kind of imagine this. This means we're going to do a 30. After 1 half-life, there would be 15. And then 7.5. And then half of this, which would be about, I believe it's going to be about 3.75, I believe. I believe that's correct. And that's how much we should get. So let's just go ahead and type it in the calculator and see if if we get that same answer. It's clear here. 30 times 0.5 raised to the third. We get 3.75. So there's 3.75 grams of iodine 131 left. And this is the proper notation when you write a chemical element. Then you write hyphen, and then you write the mass number. The mass number. Okay? Because we have to identify, because there's more than one iodine. Just like there's more than one carbon. There's carbon 12, carbon 13, carbon 14. So we actually write it with the mass number after the hyphen. Let's look at number 8. A 40-gram sample of sodium 24, Na24, has a half-life of 15 hours. How much is left after 60 grams? Well, let's figure out. Let's do 60 hours divided by the half-life of 15 hours. So how many half-lives are there? How many times will this sample of sodium-24 split? Well, 60 divided by 15 is 4. So there's going to be 4 half-lives. The starting amount is 40 grams times 0.5 raised to the 4. Now we could do this in a calculator, but we could also do this by hand. Let's see, 40. The first half-life will give us 20 grams left. The second half-life will give us 10 grams. The third half-life will give us 5 grams. So we have the first half-life, the second, and the third. And let's do one more now. After the fourth half-life, it would be half of 5, which is 2.5 grams. So we know the answer here would be 2.5 grams. And let me box the answer. So after 60 hours, or 4 half-lives, we go from a 40-gram sample to 2.5 gram sample. Well, this concludes this video.